Okay, welcome everyone. So this is the last lecture. It should be the most exciting one. Let's see. Okay, so let's start by recalling what we did the other times. Okay, let's get visibility. No, it should be. Okay. A brief recollection of what we had. So we did this definition last time, where we defined these three objects, gradually with more and more structure. So we talked about n manifolds, which were morally, you should speak of them as non-negatively graded. Meaning, or like another picture to have in mind, that you have a bunch of coordinates and they have various degrees, which are non-negative integers. And we also did a formal definition, which was that this is a supermanifold carrying an action of the monoid, of the multiplicative monoid of real numbers. And enhancing it a little bit, we NQ manifolds, where what we do, we take the previous one and we add one more structure, and that is we add a Q, which is a degree 1 vector field, which squares to the identity. And again, we said that more formally you can define this as a supermanifold with an action of the Lie supergroup of endomorphisms of the old line. But I mean, this picture is enough for us. And then finally we define this thing which I call sigma n manifolds, following the notation introduced by Pavel Shevera. Sigma n manifolds means that it's an NQ manifold with a symplectic form. So here we add degree n symplectic form, which is preserved by Q. And finally, as an accompanying notion, in the last bits, we talked about lambda structures, which is just a Lagrangian. So this is a NQ Lagrangian submanifold. It's a Lagrangian to which the Euler vector field and the Q vector field are tangent. So kind of the natural notion here. And then there was a couple of theorems we proved about these things. And one of them was that it is equivalent in the sigma n case, and you can equivalent to define this using some sort of more hands-on data. So equivalently, these are triples of n manifold with a symplectic form, and instead of vector field you specify its Hamiltonian. So you take this thing, this is a degree n symplectic form, as written there, and this is a degree n plus 1 function satisfying this equation. And one other statement that we proved, I think, at the very end was that if you have such a thing, then this thing only has coordinates in degrees up to n. So it's non-negatively graded by definition, and the symplectic form is an isomorphism on the tangent space. I mean, not the tangent with the cotangent space. So it has no coordinates of higher degree because they will be paired with coordinates of degree smaller than 0, of which there are none. Okay, so this is all that we need for today. And now let's make the following remark. this is just a tie-up what we said last time. So there's like 3 propositions I wanted to say, and then you can go to examples, which should be kind of like the culmination of where you will see how this ties up with other structures that are known. Okay, so the remarks is that if you start with an n manifold, curly m, we can define, maybe this could be a definition instead. Well, anyway, it's a remark. We define the degree 0 part, so we'll call it m subscript 0, and this is simply the action of 0 on this thing. So remember that there is an action of the semigroup of real numbers, or sorry, of the monoid of real numbers, and you can act in particular with 0. And this thing, what this thing does is you should think of this as this thing describes, or this is described by the degree 0 coordinates. So for a supermanifold, we saw that you have the even part of submanifold that embeds into the submanifold itself. In this case, there is more structure, there is an n grading, and here you also have like this degree 0 part. So, and in fact, this thing embeds via the base or the body of the supermanifold. So, we saw before that inside the supermanifold you have the even part sitting, and that's more specifically the degree 0 part. But what is a bit new here is that we also have a map in the other direction. It's a natural map. And how does this work? Like, I mean, why it's different? Like for supermanifolds, we didn't have it, but for supermanifolds, you could take 2 weird guys, you could take 2 odd coordinates, and you could multiply them to get an even coordinate. Here you can't take 2 coordinates of strictly positive degree, multiplying and get some coordinate of degree 0. So you can do that. So the fact that the grading kind of goes in one direction prohibits these kind of, allows you to make actually like say unambiguously what this map is. So this thing should have degree 0 coordinates. You know, if you pick some coordinates. Okay, so you can say that the degree 0 coordinate, well, you can say that those things are the ones, let's say here you have coordinates alpha, and let me denote, well, how should I say that? Okay, so you have here coordinates y alpha, and they fall into some subgroups. So I haven't used x, so let's say x, 1 up to blah 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 up to xn, these are degree 0. And then you have the rest, let's say z, 1 up to whatever, these are like degree bigger than 0. And this thing has only coordinates of degree 0. And what I'm saying is that there is a natural map where you just take these coordinates and you take the rest to vanish. Sorry, no, that's the map the other way, right? Okay, let's call these coordinates big X. No, that's a terrible name. W. No, let me not call it x here, y. And let's say the coordinates here are y alpha, and I simply define this map to be, this is x alpha, and that's it. So there's like x1, okay, I'm overcomplicating this. This is x1 up to yn, which is xn. This assignment defines the map that goes in this direction. And I cannot throw in any of the z's in here because the degrees will just not match. Because this needs to have the same degrees right and left, and these are degree 0. Sorry, that was a bit convoluted. But the essence is that one cannot get a degree 0 function by multiplying 2 positive ones. Yes, I'm kind of confused by the notation of saying m0 equals 0. This one? Yes. So what this means is that good. Thank you for the question. So we have a map of this R. So what does it mean to have a map of R? It means that there is a map like this. And what I'm doing here is that I'm just kind of restricting to the zero inside here. So then you get a map from M to M, and the image of that map I call it M0.
All right.
It's a bit strange if you're used to groups acting because this is a very non-invertible map, but that's because it's a monolith and not a group.
Okay. Otherwise, the image will not be interesting. If it was invertible, image would not be very interesting.
Well, I mean, the space could be interesting itself.
Yeah, but you want to define something.
Do I? No, yes, sorry. Yes, sorry. Yeah, exactly. Thank you.
So can I think of both M0 and absolute value M as just smooth manifolds?
Yes. This one definitely. And this one, yes, because it's the yes, yeah. So the fact that this actually So the first claim is that this image is actually inside this bit, and that should somehow follow from the fact that I didn't write everything up there, but there's the action such that -1 acts as parity shift on the supermanifold, and since 0 times -1 is 0. No, sorry, that doesn't help, does it? Let's see. Well, anyway, this thing should be preserved by the parity shift. Yes, the thing I said, 0 times -1 is 0, which means that the action of -1 on this thing should be this thing itself, and that should mean that it's in the body, it's preserved by the parity shift. So yes, both of them are smooth manifolds. Yeah, thanks.
But and sorry, so we have the body absolute value of M and M0, and is it true in some sense that M absolute value of M looks like M0 plus some vector bundle direction, because they should be like the other direction should be kind of all flat or whatever, because they correspond to graded, like even but graded coordinates. But it's not a vector bundle because the map goes in the wrong direction.
You mean this one or this one?
This one.
This one.
Do we have a map?
Well, this map is canonical. This map says that it's consistent to set what stuff to 0. Yeah. And sorry, what was it that you were asking?
Whether what kind of German structure is M0 included in absolute value of M? It's like an opposite of a vector bundle because because the absolute value of M should look like M0 plus some flat directions.
But this thing, but then you also have the map the other way because you embed this and then you project it down.
I see. Oh, okay.
And morally, if you think of it,
it should be a vector bundle.
Yes, but maybe even more than morally, maybe even like this.
A vector bundle.
So the thing is that the way R acts is that it kind of scales stuff.
Yeah.
So there is a
definition of a vector bundle as a manifold with some.
Yes, we looked at it today.
Okay.
But there is some technical assumptions there. So it might be more subtle, but maybe not.
Okay, thank you.
Correct. Thank you. Okay, good. So this was one remark, and then I wanted to make some sort of nice construction. So this is just to conclude the subchapter. Construction of new NQ manifolds. And there will be two general ones. One of them says, formulating the proposition, so if we start with an NQ manifold, M with Q is an NQ manifold, then so is its shifted tangent bundle with the new Q. Let's call it Q. Let's give them subscripts so that we can distinguish them. Q on T1M being the Derand differential on M plus the Lie derivative with respect to Q on M. Okay, maybe some explanations below. So now I'm taking this. Okay, let me actually explain it in the proof. So what is the proof of this? So what is this new space T shifted 1 of M? So functions. I mean, technically speaking, we really saw this before for like ordinary manifolds. But here, let me just. I mean, this is the last lecture, so let me be slightly more vague, but not too much. So functions on T1M are differential forms, which we know how to define. Differential forms on M, and on these things we have their own differential. Okay, so omega on M, and on this guy we have the Derand differential on M, and we also have a Lie derivative of with respect to a vector field. And now what is the degree of this operation? So the degree of this operation is 1. It raises the degree of the object on which it acts by 1. What is this? So the Lie derivative doesn't carry any intrinsic degree, but this thing does. So and it's of degree 1 because it was a cohomological vector field on the base. So this thing is again an operation, a derivation of degree 1. So you can add them. You get another derivation of degree 1. This is what I meant here. And now the claim is that this thing squares to 0. And so, okay, and if you just calculate that, then it breaks into 3 pieces. You will have a term which looks like this, and then you will have a term with a commutator of Lie derivatives, which just translates to the commutator of the vector fields. And all 3 of them are 0 for various reasons. Like this is by construction, that there are differential, as we saw last time. Last time, the Lie derivative is commute with D, even in gradient geometry, and this thing is just 0 by the assumption that Q squared to 0. So this thing is 0. So that's the end. This is kind of a cheap way to produce new things. And how does it look in coordinates? So, okay, let's say coordinates. So if M has coordinates y alpha, then T1M has y alpha, and then there is new guys, let's call them psi alpha, and these things have the same degree as they had before, and this thing will have degree 1 higher. That's how the shift works. 1 plus degree of y alpha. So that's one construction. And there's a second one. Position. So if M with Q is a, should I call it again? Let me call it QM. So if M with a QM is an MQ manifold, with or with coordinates for up to n, only in zero, from 0 to n, let's say in degrees up to n, then then we can construct a sigma n manifold, which is the shifted cotangent bundle of this thing. This thing is a sigma n manifold. Now I need to tell you again what. Sorry, let me just rephrase this last bit. I need to tell you what the structure is. The Hamiltonian this guy is. M, and I just claim this is Q on M. This thing is a sigma n manifold. So an NQ symplectic thing. Maybe let me first tell you what this means. So what do I mean by, so I have this new space, which I will describe in coordinates in a moment if you want. It has a symplectic form because it's a cotangent bundle. The symplectic form is of degree n, so that's fine. I will write in coordinates in a moment, but here just to say that this is just the usual thing that vector fields are linear coordinates on the cotangent bundle. Linear functions. Linear functions on the cotangent bundle. That's yeah, if you have a vector field, you can evaluate it at every point of the cotangent bundle by simply pairing the vector field with the element. And so this is an instance of that. And I think that in this case, the coordinate expression might be more enlightening. So what is happening here is that we take, let's say, as before, this thing had coordinates y. So then this whole beast, this will have coordinates y alpha. And now some complementary ones, which let's call them pi alpha. And these things were of degree, well, the same as before, some numbers. And these things will be complementary degree. So this will be n minus degree of y alpha. So that together, I can say that, for instance, the symplectic form looks like d pi alpha dx alpha, dy alpha. And if you count the degrees, so this thing has degree, whatever the degree was, and this thing has complementary degree, so that together this is of degree n. Degree n symplectic form. And similarly, you can say that the vector field q, which was qm, if you would write it on m, then it would look something like let's say q alpha depending on y times some derivatives. So when you see it as a function here, this h, this thing simply follows by, you simply replace this thing by the corresponding momentum, by the corresponding phi. And there might be some signs, and but I don't want to, okay, they are not terribly important. Depends on the way how you set it up. So, yeah. Okay, so this is what I mean. Any questions while I erase? Fairly abstract but very useful construction. Okay, so maybe a sketch of a proof. Maybe I should. There's logistics with orders on this. I want to erase this while it dries up, but if I erase it and I pull it back, then it will slide on this bottom. So, okay, let me just continue. Okay, so proof. Again, sketchy. So the idea here is that, I mean, up there I wrote it in a pretty abstract fashion, so it's this thing. Sorry. Let's calculate what Q is on this guy. Actually, there is a better way, maybe, but I'm not there yet. Okay, I can tell you the better way later on. So far, let me just say that if you calculate the Q for this H, then it turns out to be, which is by definition the Hamiltonian vector field for this function. So if you calculate what this is, then this should come out to be a Lie derivative. Acting on polyvector fields. Which is the same as functions on our cotangent bundle. Functions on T star n m. Okay, this is one way how to say that it works, and then because then the Q squared which is just 1/2 of the commutator will be just the commutator of Lie derivatives, and so it will be just the Lie derivative of Qm, which is 0. So it should again translate just to the fact that Q squared is 0. There is a sort of slicker way that I just realized as I wrote it up, but we will see that later on. Okay, any questions? So this finishes this part about the general theory, and now we will discuss examples, which is where it gets interesting, I would say. Still no questions?
Maybe
Yes?
if M is just the usual manifold, then you take the polyvector fields on that.
Yes.
I see. And why is this the degree n shift?
So it's easiest to see it from the coordinates that I erased, but
Also, actually, there will only be polyvectors for E for odd n.
oh yeah.
Otherwise, it's symmetric.
Uh,
Also, the vector.
right. Okay, right. Thank you.
And then this.
Let's say which one?
Okay, I guess you can act with the Lie bracket also on symmetric.
Yeah. So this is just powers of vector fields, or like tens of powers
contains the function.
Vector field. Right. Yes. Does this? Is this what you? No. No, but you were asking. You were asking where the degree is.
Yeah.
Or in what concretely? Like where does the?
No, maybe if you could just like unwrap the definition once again, but.
So let's do it locally. So if this guy has some coordinates like this, then this thing will have coordinates of that degree and also of degree n minus that. Which call sorry, degree alpha. Let's call those y alpha and those pi alpha. And then yeah, that's it. And so the functions of these are like stuff you can build out of these pi's and y's. And for instance, the vector field, the cohomological vector field, which before looked something like this, function of y alpha. So now we're replacing it by q alpha y and pi alpha. And the claim is that if this was degree 1, then this thing will be degree n plus 1, which is what you need for producing again something of degree 1 as a Hamiltonian vector field. And the shift should go because the shift should be there, so you need to let's just go. So this needs to be degree 1. So if y alpha was of degree, which I call degree y alpha, then this thing is of degree minus deg y alpha. So this thing should be of degree deg alpha y alpha plus 1. And if I just take it like this, and instead of doing this, I what is sorry? This is of degree 1 plus deg y alpha, and this thing was degree n minus deg y alpha. So together is degree n plus 1. Is this what you have in mind? Yeah. Okay, perfect. Yeah. Okay, now let's see the examples. So examples. The first example is, well, ordinary manifold. This is an example for Tomasz, but I forgot that Tomasz is not here today. Ordinary manifold. Wait. Now grading. I mean, trivial grading. And q equals 0. So you can take the favorite manifold like Gaussian sevenfold or something. DG Gaussian sevenfold. Okay. Now you can start applying this construction that we saw before. So for instance, you can take the example from the preceding thing and you can just hit it with this T1 functor. So you just take T1 of ordinary manifold. Let's say ordinary manifold, I will denote them by the upright ordinary letters. So this thing started as an ordinary manifold. Now after applying this thing, this is an MQ manifold with the where Q is the Derang differential. And functions are differential forms. So that's already pretty interesting. So this is an NQ manifold. Now you can iterate, or okay, you can iterate. Let's not do that, but you can also hit it with the second construction. You have already an NQ manifold, so now we can hit it with this guy. We take first this thing, and then take the cotangent stuff of the whole thing. And let's assume that n is at least 1, because I said before that you need to do this. You don't want to get negative coordinates, that's why I imposed the assumption on the theorem before. So yeah, so this is now a sigma n manifold.
Does this do things to use to convert this current?
That's a very good question. Yes, right? So there's this chain of natural isomorphisms that I think there's like 3 ways that you can write these things. You can either put actually, sorry, no. It doesn't formulate as it is, but okay. So remark. this thing, you can do T1 of T star n minus 1 of m, or you can also do T star n of T star n minus 1, I believe. Is that true?
Are you missing T, no?
No, it's do 2 T stars.
So that would be
Ah,
in
yes, yes. Okay.
I think
Yeah.
there's like natural isomorphisms between these things.
Does this have any
It's called propositional
remark?
remark, yes.
Remark.
Yeah. What do you mean the name? Like, oh, you mean like Lysander transform or something?
Yeah, or maybe, yeah.
Yeah, what?
Homotopy. No.
Maybe. Okay, now let's go in a slightly different direction. So let's take a vector space. I will call it V. And now let's see that you can regard it as a vector bundle over a point if you want. You can shift it so you get a space which looks like this. So V shifted by degree 1. And so how this worked was that explicitly, like if you pick a basis here, E alpha, then you have like linear coordinates corresponding to the dual basis, so E alpha. And so this space is described precisely by these guys, except that you assign them degree 1. This one. Okay, so we have an n manifold. It's a simple one. Now, what does it mean to have if we want to turn it into a Q manifold? So, n Q manifold. So I need to supply it with a vector field, and now we will play this following game. So, okay, the game is like, what is the only thing that you can do? Like, it needs to be, you need to have a vector field. It should be of degree 1, and the only ingredients you have are these guys, and they're partials. So you have like E alpha. And then you have a partial E alpha. This is of degree 1, this is of degree minus 1 because this removes one of them. And you should build a vector field, so you should have precisely one of these. So what is the only thing that you can do? It should be overall degree 1. So let's start with the partial. Okay, we have already something of degree minus 1. Now I want to make it the whole thing, the whole expression to be of degree 1. So what shall we do? Exactly, we multiply it by 2. Okay, thank you. By 2 e's. And then in principle you can have some coefficients, or some which if we had degree 0 coordinates they could depend on them, but we have none. We only have these things. So there is some bunch of constants here, and by index structure you can see that it looks like this. Let's put maybe 1 half or something. And this is how a general vector field of degree 1 looks like on this manifold. Now in order for it to be an NQ manifold, this vector field needs to square to 0. Okay, so what is the condition of Q squared to 0? So if you write it up, if you write it down, let me not do that. So you can or equivalently Q squared is proportional to the commutator of Q with itself. And how does the commutator work? You have the vector field. Imagine you have it twice in a row. Should I do it maybe? No. Okay. So you imagine I take the bracket of this thing with itself, and then how does the commutator work? You activate the vector field on the coefficient here, and vice versa. So you remove one of the e's. So you have 3 e's left, multiplied by some quadratic function in the f's. So you have like some, f with some indices, f with some other indices, and it's and you have 3 multiplied by 3 e's, which are anti-commute. So there is anti-symmetrization on 3 indices. And if you look at what it gives you, this is precisely the statement that this satisfies Jacobian identity. So f alpha beta gamma defines the algebra these are the structure coefficients, or maybe you could say R structure coefficients of the Lie algebra. Okay, so what does that mean? Is like take our basis and then you write it.
Does the universal enveloping algebra have some like interpretation or translation into this language?
The universal one.
Is the Kosovo dual to functions on this?
Yeah.
Sorry.
Thank you.
So can you also write it as some kind of
It's not commutative, so it will not be.
right? Yes. Yeah. Okay. Thanks.
But it's also dual to this. So if you want, it has this kind of boundary conditions in QFT interpretation.
Nice. Okay, so what is the implication? So it's Q from V1 is the same as Lie algebra structure on V. And so maybe just to go to a more familiar notation. So for any thus, I think I'm writing too large. For any Lie algebra, matrix G, we have an NQ manifold. G1. Now, okay, just maybe a side remark. So, okay, so let's unwrap, or like let's remember what does it really mean that to have a NQ structure. So we have a vector field which squares to 0, which acts on the functions in a way that it raises the degree by 1. So what are the functions on this guy? Functions on G1. These are the elements of the dual. Of the exterior power of the dual. Okay, so because functions are literal. Okay. Because functions is just a bunch of e's. E's multiplied by some numbers. So these are elements of the exterior power. And the Q that we have, that we just constructed, namely that one, together these things known as the Chevalier-Eilenberg complex. So we have an algebra with grade, we have a vector space, we have a complex, so we have like a z-graded vector space, and you have a differential acting on integer which increases the degree by 1, and if you look at what this is really the Chevalier, this is what is called typically the Chevalier-Eilenberg complex. And this thing is the Chevalier-Eilenberg differential. Okay, so one moral that we learned is that Lie algebras are secretly NQ manifolds. And in a sense, this is a sort of, well, you can argue that maybe that's a better way to even think about them in some circumstances. Because saying that something is an NQ manifold is a pretty simple.
You just need a semester of.
Yeah, but after the semester it is the most. It is the more obvious. While the Jacobi identity or the Jacobi identity, well, it's like, it's a pretty, like, why? But moreover, this thing leads to a generalization in a natural way, to which we will get in a second. But so far, I want to mention another player that you can get from the algebras. we recovered some known objects like Lie algebras and Chevalier algebra complexes. Now what we can do, we can again apply one of these constructions from before. So example, if we take our Lie algebra and apply this tangent construction, then this is an NQ manifold again. Now, what do the functions here look like? Okay, functions. So now you have two. If you pick a basis, then you will have some E alpha here, and you will have another thing, psi alpha. This thing is of degree 1. This thing is further shifted, so this is of degree 2. And so the algebra, it will be some stuff that you can build out of these two ingredients by multiplying them. These things will anti-commute, these things will commute. So what you get here is that you get a symmetric algebra on the dual tensor the antisymmetric algebra. We are symmetric, this is the symmetric powers. And again, we have a differential acting on it, which we described before in the construction. It's the Lie derivative with respect to the Chevalier-Lambert differential. So this thing is known as the Weil algebra. Or, sorry, the Weil complex, Weil algebra. It is an algebra, okay. Weil algebra. This is algebra of functions. And T1 of V. So this is another player which is a well-known construction and it's useful in many contexts. And I don't know, I can use it in localization, theory of principal bundles, other things. Here it just pops up kind of in not too difficult fashion. Okay, so what is it? Maybe one last example with the algebras. So what does it mean if you want to add a symplectic structure? So what would be a, okay, so let's build a sigma n structure on this NQ manifold. So this thing was NQ, it had a differential, it had only one coordinate, which was of only one class of coordinates of degree 1. So if we want to build an interesting sigma n structure, like the symplectic form should really be pairing the coordinates. So if this would be of degree 7, then you would need to have like coordinates of degree 6 which are paired with these ones. But if you have only coordinates of degree 1, then the only thing to get something meaningful is to have a sigma 2 structure. So let's put it here. So sigma 2 structure on here, what does it mean? So, well, it means the symplectic form. So we are looking for a symplectic form. And it should be of degree 2. So it should have precisely 2 of these guys appearing. So, well, it can be nothing else than just dE alpha, dE beta. Okay. Remember that for the counting of the recall that the degree of symplectic form was not the form degree, but it was the degree with respect to the Euler vector field. So let's say that omega was degree n if using this with the Euler vector field with n times omega. So it ignores, in other words, ignore these when they come to degree. Okay, so the only thing you can do is really to have this, and then you can put some coefficient in here. This is the general 2 form on this space. Now symplecticity should tell you that it's closed. Well, this is fortunately closed because this is independent of any coordinate. So if you hit it with a d, then it's 0. Non-degeneracy should tell you that this thing is a non-degenerate matrix. And the last condition, if you remember, was that this thing needs to be preserved by the differential. And you can see that that translates to the condition of this thing is an invariant pairing. So this is a non-invariant under the Lie algebra action. Under the adjoint action. Invariant, non-degenerate, symmetric, bilinear form. Okay, so Lie algebra together with such a thing, G plus So the thing is known. Okay, that was a terrible notation. This is what's called a quadratic Lie algebra. Oh, because okay, the obvious point which I kind of skipped over. This thing is now symmetric. Okay, sorry, should have emphasized this fact. So as objects, you see, this is of degree 1, but as a one form, I mean, the total degree of this object is 2, so it's an even object. This is even as well. So that's why this thing, if this had an anti-symmetric part, then this would vanish in the expression. So this thing is a symmetric bilinear form. Yeah. Sorry, I forgot to say the symmetry. That's kind of normally you think of symmetric forms as something anti-symmetric, but in these shifted degrees they become symmetric. Because we're used to the Cauchy rule. Okay, is that clear? Okay. Now let me. I want to say something, but I don't want to prove it. So let me just formulate it as a proposition without proof. So if we have an n manifold, if an n manifold is generated only in degrees only in degree 0 and 1, like it has only coordinates of degree 0 and 1, then in fact we have a canonical identification with a shifted vector bundle. So then it can be canonically identified with E1 or some vector bundle E over M. Okay, I mean, okay, the proof of this is not difficult. What is happening there is that if you have only coordinates of degree 0 and 1 and you want to, you want to make a change of, one way to look at it is that this really behaves like a vector bundle. So you cannot do any like non-trivial, you cannot do nonlinear changes of coordinates for these non-trivial higher degree things. You can only mix, if you make a change of coordinates, then these things are only, if you call them E, and you change to new system with new E's, then the new E should have precisely one old E. So you only So as far as these coordinates are concerned, the only allowed changes of coordinates are linear, which is the same as the behavior of a vector bundle. If you have a vector bundle, then kind of you have a natural set of coordinates which are linear, and you can transform them. They only transform linearly. So this is just to give you some glimpse of like why this is true. Okay. Well, let me just state this as a fact for now, or like forever. And now for the theorem, I think this is due to Weintraub. It says that there is a one-to-one correspondence between NQ manifolds generated in degree 0 and 1 and Lie algebras. This is kind of the ultimate meaning of a Lie algebra. It's a NQ manifold which only lives in coordinates degree 0 and 1. I can give you a sketch of the proof. So first thing to observe is that, so you remember Lie algebra, it's like Courant algebra but easier. No, that was not really the definition, but roughly speaking, it's like it has an anti-symmetric bracket satisfying Jacobi on the space of sections. Okay, so how does the proof go? So I will only sketch it, so I will show you the coordinate picture, which is still informative enough. So, proof, sketch. So we know by the proposition that, let's start with let's use the proposition. So by this proposition, every such thing looks like this. So as an n manifold, there is a unique identification with something like this. So there is a vector bundle. So if I ignore the nq, if I ignore the q, then as n manifolds generated in degree 0 and 1, they are the same as vector bundle. Now the question is, what is the differential? What is the possible vector field that I can have here of this e shifted by 1? Okay, so let's recall. This thing had two types of coordinates. E was really a vector bundle over M, and M carried some coordinates xi. So this space has coordinates xi, which are degree 0, but it also has some fiber coordinates, which are degree 1. And again, we are playing this kind of building game, where what is now the only thing that you can write is a cube with these two ingredients, and with the corresponding partial derivatives, which are this is of degree -1, and this is of degree 0. Are the rules of the game clear? We want to write a vector field, which should be of degree 1, out of these ingredients, and moreover, these things should appear only once. I mean, it should be a vector field, not a polyvector field. So, what can I do? How many of which can I put? If anyone is, oh no, okay, stop. Okay. So I need to have partials. So let's write. There will be a possible expression of this type, and then there will be a possible plus some possible expression of this type with some coefficients. Now, what are the coefficients in the first case? How many of which should I have? Where? People who are watching at home, I think that there is no audience.
You can have any number of x's.
Yes. Good. So let's ignore that.
And in the first term is the same as for the Lie algebra. So
yes, exactly. So you can have only two e's. Sorry, yeah. You need to have a coefficient which is a function of degree 2, only available of e's and x's. So it needs to represent the two of the e's and arbitrary many x's. So it will be the same as before, except now you allow this thing to depend to be a function of x. And in the second slot, this is an operator of degree 0. And it wants to be an operator of degree 1. So I need to multiply one of the e's. And I'm done. But I can in principle have some coefficients. Let's call them rho. And the coefficients can depend on x's arbitrarily because x's are of degree 0. Now, if you stare at this data that enters into this thing, then it looks suspiciously like structure coefficients. Like the Lie algebra structure coefficients, and this looks very suggestively like the anchor map which I called rho before. So now the claim is that q squared to 0 is equivalent to f and rho defining the Lie algebroid. Okay, where this f, alpha, beta, gamma, can depend on the position, is simply the bracket of e beta gamma and then paired with e alpha. And rho is simply they are the components of the anchor map. So I guess what this means is that you take your rho, apply to the base to frame e alpha at point x. Let me suppress this. here. And then you get a vector field, and then you look at an I component. So that's the plan. I mean, this was a sketch, so I'm not going to show you this, but you can believe me based on the fact that it's generalized to the algebra case, which I also didn't do. Okay, is the correspondence clear? So in some way, these are also one advantage, which I forgot to prepare in the notes, but one kind of great thing about these objects is that if you work, for instance, if you work with Lie algebroids, then there's this question of like, what does it mean? How do you define like a morphism of Lie algebroids? And well, there is a definition. If they live on the same, so it's some sort of probably it's like a vector bundle map. Let's say going over the identity, then you can kind of say what that is. But if you want to define it like you have two general Lie algebroids over different bases, then the definition of a morphism between them is kind of not that like it's like a bit lengthy or like complicated. But in this language, it's just a map of NQ manifolds. Like the natural notion of a morphism in the category of NQ manifolds is precisely the one that captures the Lie algebroids, which kind of suggests that maybe this is the way to look at things. So yeah, look, this is what I want to say about Lie algebroids. Maybe let's do one more example before the break. Any intuitions? So the map of NQ manifold, if you remember, is just a map of n manifold which preserves the q's. Or if you want a map which intertwines the action of the supermonoid. Okay, now further examples. So, okay, and here, assume for simplicity that an NQ manifold M doesn't have coordinates of degree 0. Has only coordinates of degrees 1 and higher. Okay, I will tell you the more general case in a second, but let's stick to this one for now. Okay, so what does this mean? It means that the underlying manifold M0, or not really underlying, well, the manifold M0 which we define, that this is just a point. And now let's make a choice. So pick some choice of coordinates. Pick a choice coordinates. Y alpha, which are of some degrees. They can be different degrees. Okay. And now what we're going to do is that we remember that we have a Q, and now we're going to write Q in this coordinate, and then we will expand in the Taylor series. So now expanding Q Taylor, we have, well, I will just write the Taylor expansion. So Q, it should be, in general, Q will be something like this. But if I want to expand it in Taylor, from 0, then how does this look like? So there will be, in principle, there is an absolute. So there could be like constant, potentially, maybe not. Let's see. Some number multiplying this, plus there is going to be some linear bit. So there will be like 1y partial y alpha with some coefficients. Let's call them c alpha beta. Plus there will be a quadratic bit, which will look like c alpha beta gamma, y beta, y gamma, partial y alpha, etc. Okay, okay. Now, now you might remember. Okay, remember that the coordinates are of degree 1 and more, which means the partial derivatives are of the opposite degree. So this operator here is like degree -1 or less. So because this thing needs to be of degree 1, then there is no way to achieve that by putting this, because these are just constants. Okay, so there is no, so linear term actually doesn't, sorry, the absolute term actually cannot be present. Just for purely for degree reasons. So what we have is that before I impose q squared to 0, I'm just saying that this thing gives you a bunch of numbers like this, where there will be like expressions which carry this index, structure this, etc., etc. And now this is the same as, okay, so then the condition q squared to 0 is equivalent to the fact that this bunch of things, these coefficient functions, define an L infinity algebra. Define an L infinity algebra. So those are the structure coefficients of the L infinity algebra in your basis. So if you've seen L infinity algebra before, then this might be, this is what it is. If you haven't seen it, then you can take this as a definition. It's like a, yeah. And if you've seen the definition of L infinity algebra, you might have seen it in brackets maybe, and in that case, it's kind of complicated to write down the kind of this nested structure, Jacobi identities and degrees and things, but in this language it's just this. So in this case it's a rather special infinity algebra simply for the degree reasons. So actually, this is a linear algebra, I don't know how to say, maybe let's say supported in degrees, in positive degrees or something. And maybe just elaborate, like, if you want, because I mean, so far I've been kind of coordinate-ish, so there is like a bunch of numbers, but like, really, those things, you can see them as corresponding to maps. So, maybe let me say this. So this is an L infinity algebra on the tangent space at that point. And these things will correspond to maps, to multilinear maps going from a bunch of copies of this tangent space to itself. Okay. So tangent space at this point, this is simply the thing, this is the span of all these partial y alphas. And y alphas are of different degrees, so that this is a graded vector space. It's a vector space with a grading, and you have a bunch of operations like this. And they, just by looking at the structure here, naming that these things commute or anti-commute depending on the degrees, you get some condition on the commutativity of these things. And q squared to 0 imposes a bunch of constraints, and that precisely corresponds to an L infinity algebra structure on the tangent space up there. And it's even better than that because, again, like the natural notion of a morphism of L infinity algebra is something which might look strange, like if you have an L infinity algebra, and people tell you that the natural morphisms to correspond are those that are, you don't just consider linear maps, but you consider like quadratic and cubic, and you can have all higher components. In this language, there's just, again, a morphism of NQ manifolds. And this kind of non-linearity comes from the fact that they are manifolds, and you can do non-linear changes of coordinates. So that one is kind of already subsumed in there, so it's already part of this story. So the moral of the algebra is that having a space, adding some grading, and allowing some vector field which squares to 0 is a way to go when you want to deal with many of the structures in real life, which is L infinity algebra.
When you will varize a point, your coefficients depend smoothly.
Second way?
So when you will varize a point,
Yes?
then you will have a bunch of L infinity delta points.
Yeah, you mean like, I'll admit to that now. So, yeah, I mean, if I would have, yes, if I would ignore this thing, then I would, yeah, I would just get a bunch of L infinity algebras at every point, yeah. Because the grading is set up in a way that, yeah, that you have one L infinity algebra at every point. But let me now do the kind of more general remark.
So would it be L infinity algebras or a bundle of L infinity algebras?
I don't know what the definition of an infinity algebra is, but I presume that if it exists, then it is. That's kind of how things typically go. Like if they make sense, then you should be able to see them in this language.
Okay, maybe before you do that, just a quick question. So since you have non-negative grading, this only gives you like a finite number of brackets because only a finite Taylor expansion needs to end.
Yes, that's right. That's actually a good point. I forgot. Yeah, that's right. Yeah, because all of them are degree at most one. And partial, yeah, I have finite many degrees of coordinates. I didn't say that, but of course. So there is only this thing is bounded by some number, and because these things are a degree one and more than these coefficients in this particular setup, they only can be polynomial. So those L infinite algebras will actually truncate. Yeah, there won't be brackets of too large parity. But what I want to say now is kind of the more general. Okay. Or should I leave it as a cliffhanger? Maybe after the break. Oh, okay. Maybe let me just say that okay. One thing that doing the same thing now not for MQ but for sigma n manifold. So if I throw in an invariant symplectic form. This way, the object that you get, so these brackets and the corresponding coefficient of the symplectic form, this is what is called a cyclic non-infinity algebra. The cyclic non-infinity algebra means that it's another infinity algebra which, if you see like it has a symplectic form. I mean, it's a sigma manifold. And let me leave the more general case for after the break. So let's make it a break. Okay, welcome everyone. So this is the final part of the final lecture. Yes, I promised you the earliest, never mind. Okay, so I promised the more general complex. So the best way I could come up with it is the following. Formulate as a remark. So far we've dealt with non-negatively graded manifolds. Now, okay, this is the remark about more general setup for infinite algebras. Unfortunately for this, I would need to have a Z grading. So let me just say the following words. So, assuming we define, assuming a good definition of a Z graded manifold. Sorry?
We had the same discussion. We had a similar discussion during the break.
Okay.
But this is very good. I think you will say more correct.
Sorry?
You will say more correctly.
Okay. So no, I mean I'm just assuming a definition. I'm not going to give it. Okay, so there is so people seem to approach this problem in different ways. So there's an expert here, or one of the approaches. So let me just let's just imagine that we have a similar thing. Let me not discuss the issue of like convergence or Sheafy properties or everything. Just imagine that we have a space which has coordinates of various degrees. Okay, that's what you should have in mind. So, okay, let's assume this. Now, okay, so now starting, so let me write the same stuff as above. So starting from such a Z-graded manifold, M with a differential Q. You can sometimes see people calling it a DG manifold or other names. So I want to do the same, so I need to do some choices. So the structure is that I need to pick a point. So pick a point. In the previous example, we also picked a point, and the only point that was there. Now we make a choice, so we pick a point in the degree 0 part of this thing. So again, we assume that there is sort of like a degree 0 part of this guy, described by ordinary space. Now we need to pick a point such that at that point the differential vanishes. What does it mean? You just, the point means that it's like a bunch of coordinates have some value, and if you just, if you just write this q in coordinates and you substitute those values, it should be zero. The only thing that can be.
But those like the q it also has the gradient. Like,
Yes.
And those also set to zero, right?
Yes. So q is a vector field. Yeah. With a vector. Sorry. But just. Am I incorrect? No, it's.
But like when you do it.
Oh yeah, sorry. Yeah,
practice,
right.
You also set the like not just the.
No, sorry. Yeah.
You like evaluate the degree zero coordinates numerically as a numbers, and you set other coordinates to zero.
So all positive degree coordinates set to 0.
Or non-zero coordinates. It's z grade manifold.
Yes, right. Thank you. And degree 0, degree 0 set to some values. Right. Yeah. Thank you. Yeah. And you want this to vanish. So this is first choice. My second choice is that, and we choose coordinates. Around P, and actually let's be even more, let's say centered at P, which just means that this just means that P is given by setting all the coordinates to 0. Gradient, no gradient, all of them. Okay. And if we do this, starting from this, pick a point and choose, be grammatically coherent, and choose coordinates. Okay. Then the expansion. And for laziness, I will just refer it here. Okay, let me look it up still. So then the Taylor expansion of Q. Now to recall what this was. So again, in principle, this could have a degree 0 part, but I just said that I want Q to vanish at that point, which means that the degree 0 part should be 0. Because if you set all the y's to 0, then what you get here, you get this term surviving, and I want it to be 0. So there is no absolute term. So Q simply looks like structure coefficients. Show my alpha plus C alpha beta gamma 1/2. I'm writing literally the same expressions we can refer above, etc. Defines an infinite algebra structure. On the tangent space at that point. And these things being the brackets. The unary bracket, the binary bracket, the ternary bracket. I don't know how to say the next. Quaternary. Well, quartic bracket. Okay. Okay, so and the condition, this thing was supposed to square to 0, so that condition gives you an infinity algebra structure. Okay, so this is how you can look at general L infinity algebras where you have coordinates of all degrees. Because this thing is now a Z-graded vector space.
So we could just start with like a Z-graded manifold over a point again, right? Like with a body being just a point.
Yes.
But then the degree 0 part of the algebra will be
Yes,
zero
it will be a
dimensional.
special one, yeah. But you can take like, the vector space in degree 0 if you want.
Do you know how to formulate this condition in language of function of points? Should be something.
Well, the function of points.
Yeah, because from super geometrical perspective, the setting at zeros sketch it. It's really some functorial property. It's also on the L infinity. It will be just tensoring your L infinity with some commutative algebra, which will be again L infinity.
I don't have a good answer to that. So there is like, I would say there is like several approaches how you can formalize this. And yeah, sorry. Yeah, that's why I'm hiding it inside the remark. But I wanted to say this not just because of this, but I know there is other foreign words that I can explain. So for instance, one thing that you can do is that you can look at the vanishing locus of Q. So I said that we expanded it as P, the point where this was 0. So picture to have in mind. Pictures are good. So this is your Z manifold, and there is a bunch of arrows, namely Q, and there is a point where these arrows vanish. So there's like the arrows are small around it, and as you get further, they become larger, and here they're 0. It's a very picture. So now the vanishing locus. Of Q. Well, this is just points in M0 where Q vanishes. For instance, our P. Then vanishing locus corresponds to what people call water carton elements. So if you've seen an infinity algebra definition before, then usually the way this is formulated is that you have like take some element of some particular degree, and then you plug it in like one bracket. The one bracket you put it in two places in the binary bracket, put it in all three spots of the ternary bracket, etc. Here, what does it really mean? Like if let's say I examine these points around my fixed P, so what does it mean that this thing is 0? Well, I just take partial y alpha outside, and the coefficient of that is to be 0. So for us, this is just a statement that this thing was 1/2 sin of beta gamma, y beta, y gamma, plus etc. One more. This is 0. So it's precisely the condition that you might know from L infinity algebras if you know about L infinity algebras. And maybe one more word, that's okay. Doing the same around the point where Q isn't 0, around P, such that QP isn't 0, gives what is called a curved L infinity algebra. That's another word that you might encounter in this context. So all of these things, if you like geometry, then probably the recommendation is to translate everything in this language. That's where maps are clear, and you can even draw some pictures that sort of attempt to explain what's going on. Okay, any questions? Now I want to talk about sigma and manifolds. This is the final part. So now this is the end of the remarks. So from now on we return to n manifolds. Okay, so there will be no z grading, just non-negative grading.
Can I have a stupid question?
Yeah.
So if you do this for non-graded manifolds, this triple grading, regular manifold, you can still do the expansion of the field?
Yes, but it needs to be a vector field of degree 1. Q is of degree 1.
So
if you do it in a normal manifold, then that vector field has to be 0.
On a normal vector field, and the condition squares to 0 is not very.
Yeah. So it doesn't have a kind of immediate counterpart in linear geometry, I would say. Is that what you meant, or?
Yeah, I guess. And if you go back to, I guess maybe that's what we're going to talk about now. If you go back to empty manifolds and just follow the degree zero coordinates, then
Okay.
what happens?
Yeah, then by this kind of general discussion, again, for degree reasons, every point P is good in a sense that Q vanishes at every point, simply by counting the degrees, because Q needs to be of degree 1, and yeah, there just cannot be any absolute term. So you get the same. I don't know why I mentioned to talk about that. Yeah, you only get the same thing. Sorry, but you didn't get every point, it varies smoothly, so it's maybe more structured. Yeah, any other questions? Just checking something. Okay, so now let's finish this with the discussion of sigma manifolds in lower dimensions. So we know a couple of things about sigma manifolds. So we know that they only can have coordinates of degree from 0 up to n. So now we're going to play a similar game as before. We are going to assemble some sort of Hamiltonian function and everything. And let me maybe draw a table. N manifold. And we will look at them in lower ends and see what they give you and what they give you for lambda structures. So kind of the Lagrangians. And there will be one more column which I will add. Okay, so recall what this thing was. So this was a NQ symplectic manifold. It's a differential, it's a grading, and it has a symplectic form. But equivalently, we could have described them in terms of a n-graded manifold with a symplectic form and with a function which was supposed to be of degree n plus 1, such that the classical master equation is satisfied, which is this condition with H plus 1 commute with itself. Okay, and that was it. So now, what does the, and we know, remember, and we know that this thing only has coordinates of degrees in degrees 0 up to n. Okay, so now what do we get if we take the lowest scale that we can, and if we take 0? So what does this definition reduce to? Any suggestions? I believe in.
Symplectic manifold with a Hamiltonian.
Wait.
With a Hamiltonian? Oh, no.
Good. So yes. So it's already first of all good. So there is only coordinate of degree 0. So it's like it's not ordinary manifold. Omega needs to be of degree n. In this case, it's degree 0, so it's an ordinary symplectic form. And we need to have a function of degree 0 plus 1, which is 1. But there is no such function because there is only coordinate of degree 0. So h has to be 0. So these things in degree 0 is the same as a ordinary symplectic manifold, which is just symplectic manifolds in the ordinary geometric sense. Ordinary sense. Now, lambda structure, if you remember, that was just a Lagrangian here, which was okay. Okay, the way I define it was a Lagrangian here, which was which respected to which vector field q was tangent and to which the Euler vector field was tangent. So here, well, there is no Euler vector field, I mean it's 0. There is no q because h was 0, so it's just a Lagrangian submanifold. So this is just the usual geometric setup. Okay, so this is just a warm up. There's nothing fancy happening here. So it gets a bit more interesting in case n equals 1. So
just for my, will there be something in the last column?
yes.
Thank you.
Okay, so let's talk about sigma 1 manifolds for a second. So remember there was a proposition before. So first of all, this thing has only coordinates of degrees 0 and 1. And we showed, or I mean, we stated a proposition which says that such things are canonically identified with some vector bundles shifted by 1. Vector bundle. But now we have more than that. This would be just an n manifold. But now we have a symplectic structure, and you know that symplectic structure pairs is a non-degenerate pairing of the tangent space. It should be of degree 1. So in this case, it's a pairing that kind of tells you that there's an isomorphism between the tangent space at degree 0 and at degree 1. So roughly speaking, there is as many coordinates here and here. So this vector bundle should be something whose rank is the same as the one of m, and it should have a symplectic form. So it won't be probably too surprising to say, in fact, this is not any old bundle, but our manifold, let's say, m has a canonical identification of this with a cotangent bundle of an ordinary manifold, where the symplectic form is this symplectic form. Okay, so this kind of fixes everything except now we need to talk about the vector field h. Sorry, the function h. So far we showed that if I ignore the h, then the most general such thing of degree 1 is the same as an ordinary manifold. Then we take a cotangent bundle of that, and that gives you the sigma 1 manifold. Now, if I throw in the h, if I'm now interested in h, so let's first ask the question: what are the functions on this space? Because h is a function on this space. Functions on t star 1. If you remember how these things are defined, it's you take there are sections of the exterior power of the duals. So these things are polyvector fields. Or multivector fields. On M. And also, well, okay, so for that general M, let's just simply work on this. We know that every such M is isomorphic to this, so let's just work directly on T star 1 of M. Now, this is a symplectic manifold, so it has a symplectic form, it has a Poisson bracket. What is a Poisson bracket? It's something that eats two functions and produces a third function. So in this language, it should be a device which eats two polyvector fields and produces another one. And if you remember one of the lectures from before, this looks suspiciously like a Schouten bracket, and then this is the Schouten bracket. So this thing is the Schouten bracket. There was a brief time when we discussed Schouten bracket when I defined Poisson structures. So if you don't remember that, then it's not very important because I won't be using later. Just to say that there is another notion that kind of naturally embeds into this, and with all the signs and everything, it's kind of coming just from the conventions we set for differential forms here. Okay, now what do we need? So now we're looking for a vector field, for a function which should be of degree 1 plus 1, so 2. Functions are polyvector fields. Functions of degree 2 means it's a polyvector field of degree 2, so it's a b vector field. And we are looking for a b vector field whose Poisson bracket with itself is 0, which means that we're looking for a b vector field whose Schouten bracket with itself is 0, and that's precisely the definition of a Poisson structure. So H 0 is equivalent to H in wedge 2Tm is Poisson. So here I'm going to say Poisson. There's a one-to-one correspondence between sigma 1 manifolds and Poisson structures, Poisson manifolds. Okay, if you like coordinates, then maybe we can see coordinates as well. This has some coordinates xi, this will have some coordinates, let's say pi. These are degree 0, these are degree 1, because as we said, this thing always kind of adds coefficients, if you take shifted complementary bundle, it adds coordinates of complementary dimension, such that together it's equal to 1. So degree 1. So that is dpi dxi. And this h will be something that needs to be degree 2, so it needs to have 2 of the p's, pi, pj, and there is a coefficient function depending on x. Maybe there is 1/2. So that's precisely the Poisson answer. It's antisymmetry because p's are degree 1. Now, okay, anyone wants to make a guess about what goes in the lambda structures column? It's not immediate, and I'm not going to show it. Let's say, let me make a remark here. So lambda structure should be something that's Lagrangian and that preserves the grading and the vector field Q. So let's ignore vector field Q and let's just like what is the graded Lagrangian. So Lagrangian.
I have a guess.
What's your guess?
Quasi-tropic.
Yes. So graded. So first, I'm not going to prove this thing. Just to give you the flavor. So you can show that all the graded Lagrangians here have to be of the form. So they are graded Lagrangians are conormal bundles of submanifolds. Inside M. So we have conormal bundle, which is the bundle, it's a subbundle of the cotangent bundle, restricted to S. Sorry, shifted by 1. Consisting of points that annihilate S, tangent, whatever. It's a conormal bundle. It's just some construction, and claim is that this is like 1 to 1. And the condition that this preserves the grading is the condition, actually it's the same as the condition that this function vanishes on that submanifold, which in this case translates to the coisotropic condition. So I'm not going to, we didn't define coisotropic for Poisson, but let me just, there is a notion of coisotropic submanifold.
So that will be the condition that, not that it produces grading, but that it produces that tangent,
To the Q.
differential is not.
Yes, sorry, if I said grading, I meant differential. So if I ignore differential, then I just get that graded Lagrangian submanifolds of this guy is the same as ordinary manifolds, and they, in the sense that all such things are conormal bundles of submanifolds. So for each, there is a one-to-one correspondence between graded Lagrangians there and submanifolds. And the condition that this graded Lagrangian is compatible with the differential, which is the part of the definition here. The condition singles some special submanifolds, and in this case, the condition is that they are so-called coisotropic. So I can say that means we want to say okay. So okay. Let me say here coisotropic inside Poisson means that it means that if you take the conormal bundle, the submanifold, and feed it into the Poisson vector, then it's 0. That's what it means. Or one way to say it. But anyway, ignore this. It's just more, I just wanted to fill in something in this loop. Okay, now the moment we've been waiting for is the degree 2. And so the thing to fill there is the thing that goes in here is Courant algebra. Okay, I mean obviously the list goes on, but we won't discuss it. And the thing that goes here are Dirac structures, and a bit more. Not in particular. Okay, so now how to formulate this? So this is the story of sigma manifolds. So let me formulate this as theorem. And okay, and let me attribute this theorem to like work of multiple people. So let's say this was Weintraub, Kostmann, Schwarzbach, Reutenberg, Weinstein, Schevera. Yeah, let's say that. So let me just say that there is a one-to-one correspondence between sigma 2 manifolds and Courant algebras. Again, and again, similar to the Lie algebra case, instead of giving you a proof, let me give you a. Let's play this game of building stuff out of coordinates and let's see why that actually works.
So this is an isomorphism classes, or is it still canonical? Is it just an isomorphism classes, right?
I would say it's on the object what they are, not just isomorphism classes. There is like a map. There's a procedure where you
Use equivalence of categories.
no, but there are even like for for each of these, you can like there is a well-defined construction that
Yes.
like a bijection between the two sets.
Yeah, but it's not that every coin algebra is into 4. So every sigma 2 manifold is of that 4. Is it true? It can be isomorphic to set to one of that 4, or even canonically isomorphic to one of that 4, but not.
I think there is a map. Like
Yes,
on
the map is the map is the part of the equivalence of categories. It's like you have
Yeah,
a
but it's
factor in one direction, a factor in the other direction, which also to each sigma 2 manifold you get a coin algebra, to each coin algebra you get a sigma 2 manifold. If you go there and back, you are canonically isomorphic to the original thing.
right, but the both maps are bijectionals.
I think it's a very stupid issue, but it's not true because like in the Poisson case,
Yes.
like, I guess it's not true that every manifold is T star 1 of every any sigma 1 manifold is T star 1 of manifold, but it's canonically isomorphic to one of that
So
one.
that is the question if it's canonically
It
isomorphic.
is, yeah, it's an equivalence of categories. Yeah.
Okay, sorry.
But
Then,
it
I
doesn't have to be canonical, right? If you have,
I think it is canonical. Yeah.
is it?
But
I
yeah, if you
think
think
so,
yeah.
bachelor.
The question like if you go there and back, the result will be isomorphic to the original thing. If you start with a sigma manifold,
in a canonical way.
you get a coin algebra and you go back. Yeah, so there's the natural transformation between the composition and the identity factor.
Thank you. Yeah, sorry. Yeah. Why was I thinking otherwise? Okay, okay, I agree with you, sorry. Yeah. But of course, okay, but as far as categories are concerned, we haven't really talked about morphisms of this.
And this would be only with isomorphisms.
Okay, then that's fine.
But it works for relations as well.
Okay, good. Thank you.
Maybe.
Yeah. Should. Okay, so thank you. Sorry for the confusion. Okay, so let me make a. Okay, let me again say how this works. So, and let's do the coordinates again. So, starting with sigma 2 manifold, this thing has coordinates of degree 0, 1, and 2. And the sigma 2 form is pairing these and this thing with itself. So there's sort of like an isomorphism between these tangent spaces and this one, or these graded parts of the tangent space. Now, I will, this is a sketch anyway, so I will invoke a graded Darboux theorem which tells you that actually you can pick up the coordinates in a clever way. Where you have x's and p's of degree 0 and 2, and where you have some E alpha of degree 1, such that omega takes the canonical form, which is dpi dxi. And then unfortunately this guy is paired with itself, and it's paired by symplectic form in odd degrees symmetric. So it's like you don't and symmetric. Okay, as far as canonical forms. Anyway, sorry, let me just say what I want to say. So the best I can do in that degree is that I can say that I have this where these coefficients are constant.
Split it depending on the dimension.
Yes.
And then it will be the paired with each other. If it's even dimensional, and if it's odd, you will have one pair that will give a square.
Yes, but also the signature here matters. Like it can have different signatures.
Ah, yeah, okay. I'm thinking about C equals.
That constant means independent of x.
Yes, I mean or anything.
Okay. But then can you just use some kind of spectral decomposition to get?
You mean like ones and minus ones?
Yeah.
Yeah, I could, yeah.
Okay.
I don't want to do that. Yeah, but
Yeah. Okay. One can do better than this.
One can do a bit better, but I mean this is the best as far as the notation goes. Because otherwise I would have to distinguish like minus and everything. Yeah, but you're right. You could in principle get it to like a bunch of ones and a bunch of minus ones instead of this thing. Okay, and now we have the coordinates, and now we need to build a Hamiltonian function here, h, which will be of degree 2 plus 1, so 3. And we have these only ingredients in the game. So this should not be too difficult. So what is the most general h that you can have? Well, it needs to be 3. So you can either have 3 of these, or you can have 1 of these and 1 of these, and arbitrary dependence on x. Okay, so you can either have, we're looking for functions, not vector fields, okay, so this is easier, so we don't have any partial derivatives. This is degree 3, and it can have some coefficients, let's call them C alpha beta gamma, and then it can depend here, maybe probably it's appropriate to divide it by 3 factorial, because it's antisymmetric in 3 guys, whatever. Or we can have another term, where we have a P and 1 E. And again, this is, okay, some coefficient, let's call it rho for unknown reasons, and they look like this. And okay, and what I will claim now is that these are the structure. This is the structure of the Courant algebra. Right? So this thing is simply the structure coefficient of the bracket. But now using, you see, all indices are down, so I'm using the Courant algebra pairing. Incidentally, this is the Courant algebra pairing. So this is the pairing, Courant algebra pairing. This is the structure Courant algebra coefficients. I don't want to call them constants because, well, they depend on x. Coefficients. There's 1 f, right? No, 2 f's. So thank you. Or 3? It's cubic. Yeah. Okay, so let's put another one. The coefficient. And this thing is the anchor map. Just as in the real algebra case. And the claim that you can again check in coordinates if you are brave, but we don't have to, is that the classical master equation, which is the condition of this thing, actually defines a sigma manifold. This is equivalent to the algebra, to the axioms of Courant algebra. So this is the sketch of how things go. And you see this is kind of a more minimalistic definition. It's simply a symplectic, it's a sigma 2 manifold. It's a manifold, it's symplectic formula differential. And again, for multiple purposes, if not all, this is the recommended way to go. And in fact, it can be argued that the definition of a Courant algebra should be Yes, so technically, yes, I mean, the answer is yes. Since this is supposed to be a course, I can, so there is this one axiom which is like, there's this one axiom where you have to be a bit careful. I mean, it's true, but like there's this thing where you talk about, how to take the function out. And I think that's kind of built in here, so it's, you don't see it from here, but that's simply because, I mean, I'm only giving you the coefficients here, so it kind of, I mean, I'm saying nonsense. Yeah, like to see this thing, you have to think about how to interpret this thing. Like this is really just coefficients of that. Maybe you have to check how this thing changes under change of coordinates or something like this. I mean, so but anyway, forget about it. The answer is yes. Yeah, I'm mistaken speaking. You no. Answer is yes. Thank you. Yeah. Maybe. Yeah. Answer is yes. Okay. Maybe there is a different viewpoint, which is kind of less coordinate independent. Other way to see this. From sigma 2 to Turan algebras. So suppose that we take M to be our sigma 2 manifold, and then we can start looking at functions of various degrees. So again, this is kind of like a game where I will be constructing these things. But let me write it coordinate independently. So functions of degree 0 so looking here, they will be just x, like stuff that depends on x's. So they should correspond. So I want to build this thing. I want to build the correspondence between this and this kind of vector bundle. By the way, I probably guessed this, but I didn't say this here. Like these e's, you should think of them as these are the things describing. This corresponds to the frame on your current algebras. In the same as for Lie algebras. And these are the coordinates on the base. Sorry, I forgot to say this. Or like, let's say these are linear coordinates on linear coordinates on E. Like fibrobus linear coordinates. Anyway, the same thing as for Lie algebras, except it's a bit more tricky because you have another set of coordinates which is kind of invisible in the vector bundle language, but it goes for the right. Anyway, returning to this, if I just look at functions of degree 0, it's just a bunch of these x's. So they should correspond to functions on M. Okay, so I'm building this bridge between these two things. Now functions of degree 1, they should be something that has one of the e's, and then they look like E alpha, and then there is some U alpha depending on x. And you can identify these things with let me say it here. This is functions of x, and these things will be of the form like this. So they should be sections of the dual of E in principle, but E has a pairing, so it's sections of E. So sections of the current algebroid, you can see them as functions of degree 1 on your symplectic, on your sigma 2 manifold. And maybe I can go further, so I can say degree 2, and these things, okay, this is just for experts, it won't be necessary, but this corresponds to the sections of the Atiyah algebroid of E. If you don't know what it is, don't worry. I'm just saying this is the Atiyah, the algebroid constructing for the vector bundle E with pairing. Or for the corresponding principal bundle. Anyway, that's not very important, but like how does it look in coordinates? You can either have two of the e's, so you can have E alpha, E beta, multiplied multiplied by some lambda maybe, or or you can have a something that has a single p. If you know about that Lie algebra, it has a precise parameter, right? Like a tangent vector and some element of a Lie algebra orthogonal group. Okay, anyway, the reason I'm writing this is that now we can also, okay, so we have this kind of correspondence that starting from a sigma to manifold, you can construct functions, you can cover the functions of the bases and the sections of the Courant algebra by simply looking at functions of various degrees, and then the claim, which I'm just going to write, and actually I haven't checked the signs, so this is up to signs, I'm afraid. So if you want to check what, for instance, if you want to recover the Courant bracket, or the bracket in the Courant algebra was, so you have to have some two sections, u and v. In our language, you have two functions of degree 1. And then the claim is that on the level of the sigma 2 manifold, you can recover this by taking the iterated Poisson bracket with our cliff of h. And similarly, the pairing of two sections. And if you count the degrees, it works. Like the result on the right hand side is again a function of degree 1, hence a section of the Courant. So this is how the two notions coincide. Similarly, the pairing simply corresponds to the symplectic structure. And for instance, if you would have the action of the anchor map for some section u and a function f, then you should be able to recover this. Again, I haven't double checked the signs, but this thing is called a derived bracket construction. Okay, so this is the famous correspondence.
Could you see the signature of that form on the level of Courant algebra?
Sorry?
So you have a signature.
It can be arbitrary. Arbitrary.
But can you what it tells you about your Courant algebra?
Well, it tells you the signature of it varying. What do you mean?
So we have this coefficient t alpha beta, right?
Yes?
So it's you have some pluses and minuses ones.
Yes, I mean I meant it to be general in metrics, but yeah, you can. Yeah.
So does it give you some information about your Courant algebras and properties?
Information on Courant algebra.
About corresponding Courant algebras.
Well, it just, I mean, this is the inner, that's the matrix of the inner product. That's so.
Okay.
Signature of that is the signature of the Courant algebra.
Okay.
Yeah, it's just that. There's not, yeah, nothing,
Yeah.
nothing fancy.
Mm-hmm.
Yeah, so this kind of view of Courant algebra as related symplectic manifolds is useful for various purposes. Because, for instance, people work a lot with symplectic stuff, and they know a thing or two about what to do when they are given a symplectic manifold. Like you should look at its Lagrangian submanifolds. In this case, it will be lambda structures. And here, okay, I didn't really explain, but you can probably get the feeling of why the arc structures are the thing that goes in here. And yeah, so like kind of seeing these things as symplectic kind of suggests various things to do. For instance, for symplectic manifolds, people consider categories where they consider morphisms, as was said here by Martin. You consider Lagrangian correspondences as morphisms in category symplectic manifold, or you try to consider them. And you can do the same here. So this leads to the natural notion of relations of Courant algebras and Courant algebra correspondences. And so, you know, if you prefer to work with the vector bundling, you can translate it back and you can see what it gives you. And yeah, this graded viewpoint is kind of very inspiring. Okay, so I think I have 5 minutes and I have a couple of lines I wanted to say, so I think that matches well. I wanted to explain this last column, which is empty. So I'm done. But okay, no, seriously. So Maybe let me make one remark. In ordinary geometry, if I would have a manifold and I would have a vector field which vanishes at a point, then okay, this is the point P. If I have a vector field V such that V at a point P is 0, then this thing induces an action of V on the tangent space. It's kind of a useful fact to know. So if you have a vector field vanishing at a point, then this gives you this allows you to see V acting on there. So how does that go? Well, one way to say it is that if you take any vector, let's say W here, you extend it arbitrarily to a vector field on the whole manifold or in the neighborhood, and then you take the link derivative with respect to V of this extended stuff. You get a new vector field, and then you look at it at the point P. And the claim is that this is actually independent of the extension. If and only if the vector field vanishes at 0. If you like coordinates, you can just say that you look at the vector field V, you expand it in some coordinates, and then you get something like V, I, J, Y, J, partial Y, I, plus some higher order stuff. And this is simply a randomorphism. That's the thing that acts on tangent space. Okay? The message is simply that if you have a vector field vanishing at a point, then on the tangent space you have a action of the corresponding vector field. Now, okay, I will have to do with space. Okay, now let's go back. Let's make a definition. Let M be an NQ manifold. And we define the so-called tangential cohomology. Defined at a point P in the basis of this thing, in the degree 0 part, is the cohomology of Q acting on this thing. So Q will descend because it vanishes at all points in space. It on 0. It descends to an action of the tangent space, and because Q squared to 0, also this action goes squared to 0, so it's a differential, and you have a complex. And if cohomology vanishes, if this cohomology vanishes at all points, here we say that the NQ manifold is acyclic. And so in the last column I wanted to kind of recover what the acyclicity means in these individual cases. I have 1 minute to do that. Good. So, okay. So what would it be for sigma 0? What even is the tangent space? So in sigma 0, if you look at the tangent place, in sigma 0 case we have ordinary simple manifold. So this tangent space, it will only live in 1 degree, namely degree 0, and it will look like this. It's a tangent space at 0, and so the complex will look like this. There is 0 everywhere else. And now when is the and then you have a differential on this, which is 0 because there is no Q. So the cohomology is the same as the complex. Now, when is the cohomology 0? Well, if I don't leave this thing is 0, so if the manifold is 0 dimensional. So it's something silly there. So 0 dimensional. Now for sigma 1, it's a bit more cheerful because there we saw that this is like T star. It's like T star of something. And if you unravel what it gives you in that case, you will get this kind of complex in that case. And this map here is given by the Poisson tensor. So you fill in one of the slots. Now when is this thing acyclic? Well, it's if and only if Poisson tensor is an isomorphism, so it's invertible. So the Poisson tensor is actually invertible, which is the case of symplectic manifold. Sorry, this is a bit fast, but well. And in the last case, again, claim you recover precisely this thing that we discussed when we discussed Courant algebras. You recover this sequence at point P, where all these maps is the anchor dual and the anchor. And so the acyclicity of this complex is precisely our definition of exact Courant algebras. You recover this is exact. And maybe the last line, just to tie this up with the definition. We phrase it here as a theorem. It's really the classification theorem of theorem, but it's recast in this language. So any acyclic sigma 2 manifold is isomorphic to the following thing: T star 2 T1M. So the example that we had earlier today for n equal 2, with the symplectic form given by the cotangent bundle, and with the Hamiltonian function being given by the Derham differential, plus eta, where this thing is a closed free form on M. Okay, and as my last sentence, I will just explain what I mean by this. So remember, the Derham differential is a particular type of a vector field on the cotangent bundle of M. Actually, it's the Derham for M. Derham on M. Derham on M is a vector field on T1M. Yes. And vector fields, as we know, are particular classes of functions on the cotangent bundle. So this is a particular type of functions on the ignore grading, if you want. Like it's just vector fields are elements of the cotangent bundle. So, sorry, vector fields are linear functions on the cotangent bundle.
Which is within all of that.
Yes, thank you. Function. Thank you. Yes. And what about closed tree form? So closed tree forms. Okay, so these live in tree forms on M, which are functions on T1M. And so what do I do? How do I see it as a function on the whole thing? I simply pull it back. So pull this, pull back along the projection T star 2 T1M goes to T1M. So every cotangent bundle has a projection down, and you just pull the function up. And that's how you get this. You can write in coordinates, which is probably more than likely actually less abstract. You can try doing that. Anyway, so this is kind of the final example I wanted to end with. Thank you for your attention.